So in this course, I'll discuss Markov chains. I want to keep things interactive, so I'll be asking you questions. I hope to get some responses, but please feel free to ask me as well. So I'll start with quite elementary things, but even before starting, let me just give you one question that I learned about a month ago, a question that is solved, but still it's surprising to me that questions that seem to be new about the very simple setting of Markov chains keep popping up. So here's one question. So for those who will know the preliminary material, maybe you want to think of this question. So I have a completely general Markov chain on n states. I run it in discrete time. Okay, so show that the probability starting from a vertex x that we hit a vertex y exactly at time t, for that the first visit, so tau y here, and this will be a consistent notation, is the first time, so that the Markov chain, let's call the Markov chain xj, so the Markov chain visits y. So show that this is bounded, well, by n over t. Okay, so that's kind of a riddle to begin with. Now, here there are no assumptions besides that it's a Markov chain, so it's not necessarily reversible. You can assume it's irreducible, but even that is not crucial here. So note that in this setting we cannot bound the probability that tau y is bigger than t. It's possible that the chain has a very small probability of exiting from x, that the first time we are likely to exit from x might be huge, because I didn't make any assumption on the transition probabilities here. So the starting point x might have a very high probability of just staying in place and a very small probability of going anywhere else. So you cannot have a chance in this setting to bound the probability that tau y is bigger than t. However, the probability that tau y is exactly equal to a value t is possible to bound uniformly in all possible transition probabilities. And this is a good exercise to see how well we understand Markov chains, because there is right, this has to be easy because there are no assumptions on the chain. It's not, it's not even reversible. It's not a random walk on a group. Later we'll have many more assumptions, and so we'll have tools to use. But here, there's almost no tools you can use because the setting is so general. Okay, so that's the riddle to start with. And now, mostly I'll be talking about Markov chains xj, either on finite or infinite state spaces, usually finite. The transition matrix P will be denoted like that, and so this will be the transition matrix, and we'll almost always assume, let's say we'll always assume that it's irreducible, meaning for any two states x, y, there is some time t. Our times will be discrete. So t, by t I mean an integer, so that pt xy is positive. And most, but not all of our chains will be reversible. But this is an important assumption that I will state when we make it. So a reversible chain means that, okay, what does that mean? It means that there is a probability measure pi. Okay, in the finite case, it means a probability measure. In general, there is some measure pi on the state space that satisfies pi of x pxy equals pi of y pyx for all x and y. Okay, and this assumption has several interpretations. So one which is important is that if you start the chain at a state chosen from pi, so suppose, let me add that in the finite case, we will always normalize pi. And by a measure here, this is a positive measure. So pi of x is non-negative, and in the reducible case, pi of x will be positive for all x. So that's true in general. In the finite case, we normalize pi to a probability measure. So that, so then it makes sense to think of starting from a state chosen according to pi, and then running the chain from that state. And what this assumption literally means is that if I have two observations, x0, x1, okay, where x0 is chosen according to pi, x0 has law pi, and x1 is chosen as the next state of the chain, this pair has the same law, so it's equal in distribution to x1, x0. Okay, so think about, this is just the probabilistic interpretation of this, but you can continue inductively and check, because this then implies that if you look at a longer chain, x0, x1, x2, and so on up to xk, this can also be reversed. So if you look at xk minus 1, up to x0, these two vectors have the same joint distribution in the reversible case. Okay, so you just write down what is the probability that this takes a specific probability that takes a specific sequence. So it's pi of the first element times all these transition probabilities, and this will be equal to the probability on the other side. So what this means is that if you are seeing a movie of the Markov chain evolving, and it starts as a stationary distribution and it runs for k steps, and then you take that movie and you run it backwards, these two movies have the same distribution. Okay? So that's the probabilistic interpretation. There's also an important analytic interpretation. So Hilbert space techniques are very important for Markov chains, and even in the finite case. So we can think of P as an operator acting on various spaces. The most important will be just a L2 of pi, but it actually acts on lots of spaces, so it acts, right? So just if you have a function f in L2, then you just multiply, and this way. right? And the way you should think of that is for any function f, pf tells you the expected value of the function one stage into the future. Similarly, there is an interpretation for left multiplication. So from the left, if we have a vector from the left and we multiply it by p, we think of it, the vector, as a measure. And then mu p has the interpretation if we start according to the measure mu. Mu p is the distribution one step into the future. Okay, after these kind of notations, let's already start with our first. Okay, let me give one more definition. So the total variation distance between two measures, mu and nu. So we will apply it to probability measures, and this is the supremum over all sets A of mu A minus nu A. And it has several other equivalent formulas. For instance, it's half the L2 distance. And it's also has interpretation in terms of coupling. And in the tutorial, you'll see the equivalence of all these definitions. Now, especially in the finite case, an important quantity we'll use is the distance to stationarity. So maybe let me say that in general, irreducible chains have a unique stationary distribution. And we'll call that pi. So pi p equals pi. And one thing to observe is that in the reversible case, there's no accident that we use the notation pi. So you see, in the reversible case, when you have this identity, and now you just sum this over x, then you'll get, when you sum this over x, this is just the definition of pi p is summing this over x. But when you sum this over x, this part will give you 1. So you'll get that, in particular, okay, what's called the reversing measure if exists is the stationary measure. And a very standard case of reversible Markov chains is just simple random walks on graphs. Where at every node you choose one of the neighbors equally likely. So pxy is just 1 over the degree of x if x and y are neighbors, and it's 0 otherwise. So in that case, the stationary distribution is just proportional to the degree. And to make it a probability measure, we divide by the sum of the degrees, and the sum of the degrees is just twice the number of edges. Okay, so and so the main quantity of interest, though not the only one, will be the distance to stationarity. So d of t is the maximum over starting states x of the total variation distance between the distribution at time t and pi. Okay, so again, when we start at the state x, we have a distribution which is where we are at time t. We look at the distance from that to the stationary distribution, the distance in the total variation norm, and we want to know how fast that goes down to 0. And in particular, what's called the mixing time, t mix of epsilon, is the first time where d of t is below epsilon. one easy exercise you may want to think of is, here's one exercise, the d of t is indeed monotone decreasing in t. So after the distance went below epsilon, it's not going to go above epsilon later. Okay, so in estimating mixing time is somehow remarkably rich endeavor I've learned over the last decade. Some people knew it long before. Let me say that study of Markov chains goes back, well, at least to Markov, but over much of the 20th century, finite Markov chains especially were considered kind of completely understood. In order to understand Markov chain, you just write everything in terms of the eigenvalues and the eigenvectors, and you can represent anything. And all the quantities of interest decay exponentially according to the spectral gap. So finite Markov chains were considered a completely solved area. But then there were several directions from which there was new interest in finite Markov chains. One was in statistical physics, in understanding models like the Ising model on very finite but very large state spaces. Another was just the understanding by two key people, I would say David Aldous and Percy Diaconis, who understood that if we want to understand this kind of quantity, the mixing time, the interesting asymptotics is not to drive epsilon to 0, but to think of a fixed epsilon, and understanding how this mixing time depends on the size of the chain. So let me just mention one of the many card shuffling chains we'll see later. As an example of this, take n cards in a column, and the chain goes as follows. You take the top card and put it in a random position. Okay, I'll come back to this later, but you have n cards stacked in a row, or rather in a column. Okay, now you take the top card and you insert it in a random location. After you remove the top card, there are n possible locations you could insert it back. So this defines a Markov chain on the permutation group, because I can think of starting and the cards labeled 1, 2, 3 up to n, and this move of taking the top card and putting it in a random position defines a transition matrix on the group of permutations. It's a way to go from one permutation to another. So how long does this Markov chain take to mix? So the question is, so take any epsilon here, and we'll usually, epsilon equals a quarter will be a value we will focus on, but it turns out to be not important. As long as the epsilon is less than a half, then these t mix of epsilon are all equivalent up to constant. So epsilon equals a quarter will be a convenient case. So suppose you want to get within a quarter of the stationary distribution. How long does it take on this chain on the permutation group? So this is one of the problems we'll see solved later today. Okay, so this will be a key focus. Another key focus, which I'll focus on more this morning, will be rate of escape, and I'll want to connect these two. So I said mixing times are important, and I was summarizing from the interest from statistical physics. Aldous and Diaconis, who realized the right kind of asymptotics to look at was large state spaces and fixed epsilon, rather than fixed state space and driving epsilon to 0. And so that was in the early 80s, and in the late 80s, a great interest emerged from theoretical computer science, where randomized algorithms based on running Markov chains came into prominence in order to sample and count large combinatorial state spaces, for instance, all the proper colorings of a large graph. So, or all the matchings in a large graph. And all these kind of streams of thought had influenced each other and started merging in the 90s. And there's a lot more going on in this today. So besides mixing time, one other theme I'll emphasize is rate of escape. And let me start discussing that. And these will connect closely. So now let's focus on a simple random walk on a graph. And I'll call rho of xy will be the graph metric. So the graph distance is just the length of the shortest path in the graph between x and y. Okay? Shortest, so the number of edges in the shortest path. Okay? And a key quantity we look at is the distance between the starting point x0 and the chain at time t. I want to see how fast that grows and how fast also the second moment of that grows. You saw some reference to related quantities in Greg's talk, where the emphasis was on processes in standard lattice but non-standard walks. Here we'll be talking about standard random walks, but in a larger variety of graphs. This will generally be an easier topic. So let's start with the distance itself. And maybe the first question is the expected distance. First question, is the expected distance monotone? Well, let's first rule out some trivial obstructions. So for instance, if our graph has one edge and we're just going back and forth across the edge, right? At time 1 the distance is 1, at time 2 the distance is back to 0. So there can be a parity issue. So let me ask, is this monotone when we restrict for even times t? So let's avoid the possible parity issue by just considering even times. Is the expected distance monotone? Again, I'm considering simple random walk on a graph, which is in particular reversible. In the non-reversible case, it's very easy to construct non-monotone examples, but here we are in a reversible setting. Well, still the answer, so I didn't say how we start, so if we just start at a fixed state x, the answer is still clearly the distance is, okay, maybe you have to think for a few minutes, clearly the distance is not, doesn't have to be monotone. Here's a kind of example. So take a binary tree of a few levels, and now connect all the nodes on the boundary on the level k to one special node, and now add another edge from the root to the special node. Okay, so it's easy to draw small examples, but I want to actually give you a class of examples that show the distance is highly non-monotone. So what's going to happen here when we start at the root over here? Well, there's some chance we'll go immediately to this special node, but there's a substantial chance we won't, and we'll just go down this binary tree. In fact, you can calculate it with probability at least a half. You'll go down, probability bigger than half. You'll go down to this binary tree, and then and then once you're here, you could step to this special node. So you see that. So this binary tree, I drew it of depth 3, but you could draw it of any height h. And then what's going to happen is that the distance from the root, if you look at time, say h over 2, the expected distance from the root will be order h. But if you look at very large times, what's going to happen? If you look at time h squared, for instance, then it's very, very likely either you went to this node or you went down the tree and reached this node. And then once you reach this node is because it has such high degree, it's a very strong attractor. It has most of the stationary distribution. And basically, once you reach this node, you're going to make small excursions back and forth to this node. So once you reach this node, you tend to stay nearby the node. And so the expected distance will go up and then down. It will go up to order h and then down to order 1. OK, but this was because we started at this very special node. So now I want to make this question more interesting by suppose that we start not at a fixed vertex x, but suppose we start at a node x0, which is chosen according to pi, according to the stationary distribution, which is just means proportional to the degrees. Okay, now we have a somewhat more interesting question. And if we can see that, let's make things even more extreme, which is, suppose the graph is transitive. So here's a special case. Suppose G is transitive. What this means is for any two vertices x and y, there is some graph automorphism psi from the vertex set of G to itself with psi of x equals y. So transitive graphs, intuitively, they look the same from any vertex. For any two vertices, the geometry looks the same. And the formal definition is for any two nodes, there is a mapping that takes x to y. And it's a mapping of the vertices. It's invertible. And it preserves adjacency. That's what graph automorphism means. So if x and z are adjacent, or if z and w are adjacent, then their images are adjacent. And it's if and only if. So graph automorphism means z and w are adjacent if and only if psi of z and psi w are adjacent. Okay? So these are transitive graphs. And in transitive graphs, if I look at a quantity like the distance from x0 to xt, and I look at the distribution of that or the expectation of that, it clearly doesn't depend on the starting vertex because all starting vertices will be the same. So in the transitive case, is it true that the expected distance is increasing? Okay, who thinks there's a counterexample in the transitive case? Okay, how?
Maybe the triangle.
The triangle.
No, okay, it's similar to the triangle, but the triangle is the same. Yes, the triangle.
So remember, we're only looking at even times. What?
The square, and you always go to the next one.
Right. That's not a simple random walk on a graph. That's not reversible. Okay. So Okay, here's so I remember thinking of this question and not seeing a solution. Here's a very simple example, which is actually was in an email from Oded Schramm back in 2005, and it goes like this. Take a large cycle. So this example will be a little different because it will be a graph, but it will have multiple edges. So later I'll ask you for an example without multiple edges, but in this one, you start with a cycle. So the cycle has n nodes, but every edge is repeated many times, say 2 to the n times. Okay, and okay, I'm not going to draw all of these. So every edge along the cycle is repeated 2 to the n times. In addition, we're going to add some long edges. So every node will be connected to all the nodes. So every x, y with distance, with cycle distance greater than root n have an edge. Okay, so here is a specific vertex x. I connected with all the y's that are far away on the cycle. How far? Further than root n. Okay, and there's a lot of freedom in this definition, but this is a specific definition. And note that I do it for all x's. I'm not going to draw it because it will be a mess. But this defines a transitive graph because I do the same for all the vertices. Okay? Is the definition of the graph clear? This is a graph. It's not a simple graph because these edges are repeated. But it's a graph. And now let's understand how does the distance behave in this graph. So first of all, this graph has diameter 2. Because any two nodes, either they're neighbors, or if they're not neighbors, say this x and this z, they're not neighbors, but you can connect them by just going from x to a faraway point here and then back to z. Okay? So this graph has diameter 2, meaning any two nodes can be connected by at most 2 edges. How does the random walk behave? You start here. The expected distance from the starting point initially is 0. Now if I look at the expected distance at time root n, right? So if I look at the expected distance from x0 to x at time root n, and let me write rho, the graph distance. Well, at time root n, the probability we are at the starting point is pretty small, and that we're at any of its neighbors on the cycle. On the other hand, we haven't yet reached the faraway part of the cycle, so this expected distance will be about 2. 2 up to a correction which is little o of 1 as n tends to infinity. So at time root n, the distance is very close to 2, and it will tend to 2 if you let n tend to infinity in this picture. Okay, because most of the distribution is spread out on vertices that are graph distance 2 from the starting point. But if I look at, so the important thing to note here is that these long edges, they affect the distance in the graph, but they don't affect the walk for a long time, because every edge here has multiplicity 2 to the n, so along the cycle, while these long edges have multiplicity 1. So when I choose where to go, the chance I'll take one of the long edges is tiny. It's, right, it's n over, less than n over 2 to the n. So until, so if I'm asking anything until time, say, 1.5 to the n, the chance I see any of these long edges in my walk is exponentially small. So I'm really just walking along the cycle, and the long edges are just changing the metric. Okay? And so the distance at time root n will be about 2. The distance, now if I look at a much larger time, say a time n squared, by time n squared, the random walk on the cycle has spread approximately uniformly along the cycle. And so the probability we are in the root n distance, cycle distance root n from the starting point, that probability is pretty small. It's some constant over root n. And with very high probability, we're somewhere far away on the cycle, which has distance 1 from the starting point. So this distance, expected distance at time n squared, is about 1, with a correction which is little o of 1. So we see that the expected distance function, it started at, of course, it starts at 0. It went up to almost 2. And then it went down to almost 1. So that was Oded's example, and that left 2 questions, which I want to leave you with and I'll come back to. One is, can you make an example like this with a simple graph, with a simple transitive graph? So a graph where all the edges, there are no multiple edges.
Why it's not taking squared steps?
Okay.
So is it not always way?
So it's not always the way. So if you, all right. So if you look at time, okay. So as we said, this walk is going to be at this time behave like the walk on the cycle. Now, if we want to understand the walk on the cycle, we can think of it as the walk on the integers mod n. Now, if we go in the integers, if we go for time n squared, we know that the probability, well, if we go for any time t, we know that the probability to be at any specific point is at most constant over root t. Right? So,
won't n steps be enough essentially? Well, a little bit more than n.
yes, a little bit, well, a large constant times n will be enough here. But, you know, I'm not trying to be efficient in this example. I'm just trying to give an example. So one thing, you know, here the distance went down, but by a factor 2. Can you make an example where the distance will go down by 4, by something unbounded? Can you make an example of a simple graph?
If we replace this by a product of very large complete graphs, the power and this cycle, and then join
Okay. So
second.
anyway, so for a long time I knew this example, and so for a simple graph I can make from it an example where the ratio goes down to by a factor 3/2. So in other words, the expected distance at some time is large, and then it goes down to 2/3 of that. I cannot make a simple graph where we go down by a factor 2. So if you want, I don't consider that an important question, but still, you know, if anyone can make an example like this where the distance will go down by 2, I'd be interested to see. I can only make the distance go down by 3/2 if I insist on it being a simple transitive graph, no multiple edges. And the other question is, well, is this 2? I mean, once you came up with an example of 2, maybe just by taking some kind of fancy product of it, you can get 4 and 8 and so on. And I tried to do that, and I couldn't. And actually, there is a very simple argument, but still neat. So maybe I'll give this as an exercise for later, that the 2 here is optimal. So Here's a little exercise, and the solution is, the proof is due to Mark Braverman. Now, you won't find it in any of these papers because this is something he did over lunch, but it's still a neat fact. So it says if you have t bigger than k, both even, and I have a reversible Markov chain, then the expectation of the distance from x0 to xt is at least half the expected distance from x0 to xk. This is for any reversible chain. Okay, so you have a reversible chain. So more general setting, it doesn't have to be a transitive graph, it doesn't have to be a simple graph. Any reversible chain, you look at the distance at time t, and you compare that to the distance at time k. If t is bigger than k, the distance can go down, but Oded's example is optimal. You cannot go down by more than a factor of 2. Okay, so exercise to think about. All right, so I want to see that even on very simple questions of the distance, there are some surprising things. And now I want to move to more maybe serious issues. So I want to relate the distance to the diameter of the graph. I mean, I want to relate mixing times to the diameter of the graph. And so here's a little theorem. I'll show you it's immediate from a theorem of Valpolus and Karn. And it says that for for simple random walk on a simple graph, the mixing time is always at least the diameter squared over log n, with the universal constant here, which will determine like 1/8 will work. So when I don't write, I mean a quarter, but we'll see it's actually going to be true for any level provided n is large enough. So I'm going to take n large. So n equals 2 or 3 might be a counterexample, but I'm not concerned with very small n here. Okay, so yes. Thank you. N is the number of vertices. Thanks. N is the number of vertices in the graph. Okay, so You see, on a graph like the cycle, the mixing time is diameter squared. And that's one theme I want to explore with you, how the mixing time is in general related to the diameter squared. The fascinating open issue there relates to the upper bound in the transitive case, and I'll come to that. But let me first do the lower bound, which holds in general, but with a correction of log n. So you see, there are graphs where the mixing time is faster than the diameter squared. Like if you take what's known as an expander graph, some of you have seen it. So there are graphs of size n that are even 3 regular. And these graphs, so for expander graphs, the diameter is log n and the mixing time is log n. So let me mention kind of a trivial bound, that the mixing time at any level is at least the diameter it's at least half the diameter. And that's really a trivial bound, because if you think of two initial states, x and z, whose distance is the diameter, and you look at the time, which is, right, so if the distance from x to z is this diameter, and you look at the time t, which is half the diameter, then if you look at the distance pt x dot minus pt z dot, this total variation distance will be 1, because these two distributions are going to be supported on disjoint sets. So this total variation distance will be 1. So of course it's impossible that the distance to pi will be a quarter, because total variation distance is a norm, right? So this is less than the distance from this measure to pi plus the distance from this measure to pi. So if this distance is so large, it means that what we called before d of t must be at least a half. Yes, question?
Do you mean actually 2?
No, so the total variation norm is half the L1 norm. Okay? All right? So this is the trivial bound. This is somehow a non-trivial bound, which is in almost all interesting cases, it's an improvement. So, all right, so let's prove this. And along the way, again, what I'm most interested is on upper bounds of this nature that involve the diameter squared. But on the way, you'll see this Valpolus current bound, which is already, more than 20 years old, but still, is well known, but should be more well known. So what is the Valpolus current bound? It says that for reversible chains, the transition probability at time t is bounded by, well, it's bounded by the probability that a simple random walk at time, okay, and this is a simple random walk on z. A simple random walk started at 0 will go to distance which is bigger than the distance from x to y. And this we can easily bound by, say, twice e to the minus rho squared of xy over 2t. Okay, so again, what here on the top, ST is just simple random walk on the integers going plus or minus 1. And they ask, what's the chance that the simple random walk at time t will go to distance? And I'm sorry, and then in the general case, I'm missing some factor, which I should add here. Square root pi y over pi x. Sorry about that. Okay, so there is this initial factor on the outside, which, so if the graph, if all the degrees are the same, then you don't see that factor. In general, you have that factor. Then this probability, this is simple random walk in the integers to go distance bigger than rho xy. This is a remarkably effective and powerful bound in many settings. It was first proved by Valpolus in a weaker form by relating the random walk to Brownian motion on a suitable manifold, and then somehow the canonical proof was found by Keith Karn directly on the graph, but very much inspired by Valpolus' original proof. All right, so once you have, we'll focus on this bound. Once you have that, going from here to here is just the standard large deviation bound for simple random walk, which you can get from Stirling formula or from any method, Chernoff bound, Hofding-Azuma inequality. Bernstein is maybe the first to prove a bound of this type. So this is just the bound for the tail of the binomial distribution going from here to here. But this inequality relating completely general Markov chain to random walk on integers is, I think, quite surprising. So let's, yes, question?
Does the constant C over there in the theorem, previous theorem,
yeah,
does that depend on graph?
No. Okay, 1/8 will work. Okay, so, all right, so let's prove this bound and see how it implies the diameter bound up there. So, all right, so we need some basic facts about the spectrum of P. So the eigenvalues of P are all real because it's self-adjoint. So it's a self-adjoint operator, and they're all in -1, 1. So this you can see because, for instance, I mean, you know it, but one easy way to prove it is to observe that because P is a stochastic matrix, for any function f, the L infinity norm of Pf is certainly bounded by the L infinity norm of f, just because it's an average. And this means that you could not have an eigenfunction with an eigenvalue bigger than 1. So the eigenvalues are in -1, 1. So and the eigenvectors are orthogonal. So if you represent the P in the eigenbasis, you will get a matrix, just a diagonal matrix, where the top eigenvalue lambda 1 is always 1. We arrange these eigenvalues in decreasing order, and it's strictly bigger than the second eigenvalue lambda 2. To lambda n. Note that 1 is always an eigenvalue because the function 1 is a fixed point of P. All right, so with that in mind, okay, the proof, I'll show you the proof. It's very short, but somewhat miraculous if you don't know where it comes from. So the proof uses Chebyshev polynomials. So defined by qk of cosine theta is cosine k theta. Now, I'm not going to assume that you know anything about Chebyshev polynomials. What we don't need really anything about them except what follows easily from the definition. So we're going to develop what we need. So what do we see from this Okay, so with apologies to the analysis experts, but I have to spend a minute on. So because cosine alpha plus beta plus cosine alpha minus beta equals to cosine alpha cosine beta, you get the formula that qk plus 1, say qk plus 1 of z equals 2z times qk of z minus qk minus 1 of z. And of course, you see that q1 of z is z, q2 of z is 2z squared, and minus 1. So, and right, q0 is identically 1. Anyway, so from this recursion, you see that q's are indeed polynomials. Right? You see this by induction from here that they're indeed polynomials, and qk is a polynomial of degree k. Now, the other important thing to observe is that because we know cosine is bounded by 1, if z is a real number in minus 1, 1, then qk of z is also in minus 1, 1. Because, well, z can be written as a cosine. So the way we will use it is to say that the operator norm of qk of p, so this is the norm of it acting on L2, is at most 1. So what's going on here is for A, which is self-adjoint, the operator norm is just the largest eigenvalue in absolute value. Okay, so it's the absolute value of the largest eigenvalue, okay, in the maximal absolute value of an eigenvalue. And so if you want to think of, so this is a very standard fact, if you want to think of it in an elementary way, think of writing p in this eigenbasis of lambda 1 to lambda n, and then you write it this way in the eigenbasis, and you observe that since qk of p is a polynomial in p, it has the same eigenfunctions, and the eigenvalues are just qk of lambda, where lambda ranges over the eigenvalues of p. So to apply qk to p, you just keep the same eigenfunctions and apply qk to the eigenvalues. So if the eigenvalues were in minus 1, 1, that's also true for qk. And if all the eigenvalues are in minus 1, 1, you can in an elementary way calculate the norm, and you see that it's still in minus 1, 1. So the norm of this as an operator acting on L2 is at most 1.
Exactly 1?
Yes. So I mean, in this case, because if you take the function if you take the function 1, so just take the function which is identically 1, and you'll see that it's exactly 1. Okay, so how are we going to use that? So let's start with a simple identity. So we take z to be cosine theta, so e to the I theta. So cosine theta, which is z, I write it in this form, e to the minus I theta over 2. And then I take z to the power t, where t is an integer. And you can think of this as a binomial expansion, but I want to write it in terms of simple random walk. So it's sum k from minus t to t of the probability that s t equals k. Okay, so you can think of this as binomial expansion, but it's even simpler if you think of it in terms of the proof of the binomial expansion, because you can just think of writing t copies of this z, right? You write it t times, and then when you want to multiply it out, what is multiplying out? You have to choose in each parenthesis. Are you going to, in each parenthesis we have this e to the I theta plus e to the minus I theta over 2. You have to choose, are you going to choose the left or the right? So that's like the choices of the random walk. Is it going to go up or down? And you have exactly t such choices, so that corresponds to the random walk going to time t. And if the random walk reached height k at time t, it exactly corresponds to the product of terms that leads to e to the I k theta. So this is just follows by multiplying this out, or if you want, it's the binomial. It's a way to rewrite the binomial expansion. Okay, so now this is true, and let's write it. It will be convenient to denote q minus k equals qk. Now the term for k and the term for minus k here are obviously the same by symmetry. So I can replace this by the sum with cosine k theta. And then remember that cosine k theta is just qk of z. Okay, so z has this expansion in terms of the Chebyshev, z to the t has these expansions in terms of the Chebyshev polynomials. And since it's true for a variable z, it's also true if I plug in the operator p into this identity. So I get that p to the t equals the sum over all k of the probability that st equals k times qk of p. Okay, I'm going to erase this, this important fact, but that the norm is at most 1. We're going to use it. Okay, now we want to take this identity and plug in, look at the entry xy corresponding to this tth power. So first let's observe what's qk of xy. Qk of xy we can write as delta x. This is just the indicator of x times qk applied. The matrix qk is multiplied by delta y. And we're taking inner product always in L2 of pi, so we have to normalize by pi of x. Because when we take inner product in L2 of pi, we're going to multiply by a pi of x, which we have to remove. So this is just an identity. And now we use Cauchy-Schwarz to bound this by the norm of delta x times the norm of this. Again, the norm here is in L2 of pi. Okay, so QKP, thank you. Thanks. Right, QK of P is the matrix applied to xy. Thank you. So we have this product. Now, okay, now we want to use Cauchy-Schwarz. So it's norm delta x times the norm of this vector. But qk of p, we already know that its norm is at most 1. So we can write here the norm of delta y divided by pi of x. And now what's the norm of delta x? It's just the square root pi x. So what we get here is the square root of pi y over square root of pi x. So after this observation, we just plug into this identity. So we get p to the t xy is, is bounded by the sum probability of st equals k times root pi y over pi x. But there's one crucial step here. On which k do I need to sum? Well, the point is that qk is a kth degree polynomial. So qk of p only involves a sum of powers up to the level k. So I just have to sum here over k, which is bigger in absolute value than rho of xy. Because for k which is smaller than the distance, then of course for k which is smaller than the distance, pk of xy is 0. And it follows that qkp of xy is 0 because qk of p is just a linear combinations of lower powers of p. It's a polynomial. So this will vanish for k which is smaller. So in this sum, we only have to take terms which are bigger than the distance between x and y, the graph distance. Okay? This is a crucial point where we use the fact that x and y are far. Any questions? Everything clear? All right. So I'm erasing. Please. All right. So by the way, this proof you can find in Karn's original paper, and with this exact notation, you can find it in my online book with Russ Lyon's probability on trees and networks, if you want to look it up. So, all right, so now let's see how we get this bounds for mixing time. Again, take two vertices, say x and z, where the distance from x to z is the diameter. So I'll denote it by capital D. That's the diameter of the graph G. And let's look at the set A, which are all vertices V, so that the distance from V to X is, say, at most D over 2. Now what's the probability starting at x that at time t we're outside A, we're in A complement? Okay, so we're going to use the Valpolus current bound. So the first term, root pi x over pi y, root pi y over pi x. Okay, let me write it. It's the sum over all v in A complement right of p to the t xv. So we have the factor 2. Now root pi y over pi x, the worst it could be is root n. Now let's sum over the number of vertices in A complement. Well, that's at most n. So that takes care of this sum. And then we have e to the minus now the vertices in A complement have distance bigger than d over 2, so we get d squared over 8t. All right, so now any questions about this? So now let's just take a suitable choice here, say t squared over 16 log n. So the probability we are in A complement is going to be bounded by n to the 3/2 from here times, well, what happens when we, the time, okay, so when we plug in this time, so the d squared and the 16 will exactly cancel, and we'll get e to the minus 2 log n, which is just n to the minus 2. So we'll get 1 over root n as an upper bound. Okay, so you see that the probability if I look at the probability that xt is in A and I compare it to the probability starting from z that xt is in A, this is bigger than 1 minus 2 over root n. Yeah, okay. So, right, is everything clear here? So, because starting from z, we have the same logic tells us that the probability we are in A is less than root n. And this probability is bigger than 1 minus 1 over root n. So we get this bound, which tells us that the total variation distance between starting at x and z is near 1. So the total variation distance from one of them to pi has to be at least a half minus a small correction. So that implies that bound with t mix of a quarter, really t mix of any number less than a half, and the constant c, which is 1 over 16. Okay, so we'll continue later with the upper bounds in terms of diameter where there's significant open problems. Thank you.